Hello dear students, in this subject hydraulic engineering. Today we'll start a new chapter, that is boundary layer theory. In this chapter we'll discuss the concept behind this theory, the characteristic of this boundary layer, okay, momentum, integral momentum equations on set turbulence, properties of the turbulent flow, skin friction, drag force, lift force and circulation. These things we will discuss in this chapter. But this boundary layer theory, what is this boundary layer? Okay, uh, this simply saying this layer, this is the layer of fluid. Okay, when actually the fluid passes through a boundary of any solid body. Okay, or in case of open channel or river, it is the bed, river bed is the boundary or bank is the boundary. Okay, so when it passes a boundary like here in this figure, so there will be some impact of this boundary on the flow. Okay, the layer on which there will be impact, okay, that layer is called boundary layer. Now what will be impact? The impact will be the reduction of the velocity. And at this contact of the boundary surface, the fluid velocity will be 0 if the boundary is at rest. If this solid body is not moving, it is at rest, and the boundary surface is at rest, then the fluid layer which is in contact with this boundary will have 0 velocity. Okay, initially it is flowing at u velocity, but here at this layer there will be reduction of velocity or retardation of the this flow. So this layer, okay, on which there will be impact of the boundary surface, this layer is called boundary layer. It is introduced by this L. Prandtl in 1904, and this boundary layer theory is applied in various branches like in open channel flow, okay, lubrication, means you can say mechanical engineering, chemical engineering, aeronautical engineering, okay, all these branches apply this uses this theory. And the main concept is that when viscous fluid flows past a stationary solid boundary, a layer of fluid which comes in contact, the layer of fluid which comes in contact with the boundary surface adheres to it, and condition of no slip occurs. Adheres to it means if it is at rest, then the velocity will be 0 here. If this body is moving at some velocity, then the fluid velocity at the contact will be same as the boundary layer velocity. Adheres to means the velocity of fluid at the contact will be same as the fluid velocity of the boundary surface. If it is 0, then that will be 0. If velocity, then there will be a same velocity. And the viscous force dominates the inertia force. Here at the boundary, the viscous force is more important. That actually dominates the inertia force. Due to that, boundary layer occur, means there will be impact. And condition of no slip occurs. What is no slip occurs? No slip means no slip condition. It means that I told that it means the velocity of fluid at a solid boundary must be same as that of boundary itself. Let this is the boundary, this is the plate. If this plate is moving at some velocity, the velocity of fluid at the contact at here, it will be same as this plate velocity. If it is not moving, if it has at rest, then here velocity will be 0. Okay. Thus the layer of fluid which cannot slip away from boundary surface undergoes retardation. Can't slip away means this boundary cannot take this flow. That means there will be some velocity even if it is at rest. Okay, this boundary is at rest, there will be some velocity of this boundary layer. But that will be, the flow will be retarded. Initially, originally before this boundary layer flow is flowing, the velocity is u, and when it meets, the velocity reduces. Thus, the layer of fluid can't slip away from the boundary surface, undergoes retardation. It undergoes retardation, means this layer undergoes retardation. This retarded layer of fluid thereby developing a small region in the immediate vicinity of the boundary surface. In the immediate vicinity of the boundary surface, means here in this region. Okay. This retarded layer of fluid thereby developing a small region in immediate vicinity of the boundary surface is called boundary layer. This layer, okay, in the immediate vicinity of this boundary, okay, where retardation occur is called boundary layer. Means here the velocity is less than this u, which is the original velocity before meeting the boundary. The flow velocity increases from 0 at the boundary surface and approaches the velocity of the mainstream. Okay, at this boundary layer, just beyond this boundary layer, the velocity approaches its mainstream velocity, that is free stream velocity u, which is before this meeting this boundary. Okay, from 0 to u. Next is the characteristics of this boundary layer. This is the one plate here. This is the boundary. Okay, and this is the flow velocity with u. Okay, so when it meet, there will be boundary layer. The boundary layer thickness, this layer. Okay, at this point, this is the thickness. This distance, this thickness is called boundary layer thickness or the delta. Okay, this thickness or delta increases as distance from the leading edge increases. Leading edge x, okay, x increases. When x value increases, means toward this direction, okay, it increases. This delta value increases gradually here. Rear edge means this edge is called trailing edge, and this leading edge, the front edge, is called leading edge. At the front edge, it is called leading edge. As the distance from the leading edge increases, the delta value increases gradually. Delta decreases as u increases. Delta increases as viscosity increases. As I told, the viscosity is the main force here. Actually, there is total two force: viscous force and inertia force. So here, this boundary layer is due to the viscous force. But if velocity increases, if u increases, then the impact of this viscous force will be reduces. Okay, actually this boundary layer is theory due to the viscosity. If the velocity increases, velocity will be very high, it will be increases, the impact of this viscosity will reduces. So the delta value gradually decreases. The delta value gradually decreases as u increases. But if delta increases, viscosity increases. Okay, let at this point of time, let its u is 10 meter per second, it is flowing, and these are the thickness, boundary layer thickness at this point, let it is the boundary layer thickness. And if it is moving at 20 meter per second, okay, in the second case, if it is moving at 20 meters per second, then this will be like this. Okay, it will decrease. Okay, this will be a new that boundary layer thickness. That will decrease because the impact of the viscosity decreases if u increases. As far as viscosity is increases, the delta value increases, and then shear stress we know that is mu into u by delta, and where mu this is the new kinematic viscosity, and this shear stress decreases as x increases. As x increases, the shear stress gradually increases. Because delta decreases, u increases, that's why shear stress increases. Near the leading edge, the boundary layer is usually laminar. Here, the boundary layer is usually laminar. As x increases, more and more fluid is slowed down by the viscous boundary. As x increases, the more fluid is slowed down by the viscous boundary. The fluid becomes unstable and breaks into turbulent boundary layer over a transition region. Like here, this is the turbulent region. As x increases, so here the fluid will become unstable, and it becomes the fluid motion will be here in zigzag manner. Okay, So here at this point the flow will be like this. Okay, it will be here it will be turbulent region, turbulent boundary layer. For a turbulent boundary layer, if a boundary is smooth, the roughness coprojection are covered by a thin layer which remains laminar called laminar sublayer. Okay, as you discussed, the already we discussed that smooth boundary and rough boundary. In the this turbulent boundary, if this surface, the boundary surface is smooth, then there will be a laminar sublayer. If boundary layer is rough, then there will be no laminar sublayer. If the boundary is smooth, then there will be layer here. Okay, small layer near the boundary that is called viscous sublayer or laminar sublayer. Okay, this boundary layer on this flat plate are function of a flat plate is function of ux by nu, where nu is the kinetic viscosity, u is the flow velocity, that is the free stream velocity, x is the distance from leading edge. If this ux by nu, if this value will be less than 5 lakhs, 5 into 10 to the power 5, then the boundary layer is called laminar boundary layer, and the distribution will be distribution, velocity distribution will be parabolic. However, if it is more than this 5 into 10 to the power 5 ux by nu, then the boundary layer is turbulent boundary layer and the distribution is logarithmic. Okay, like it is shown here. It is logarithmic boundary, here it is parabolic laminar layer. So it depends upon the x, u and nu. Okay. Okay, this is the boundary layer thickness, which is considered as boundary layer thickness, which is delta exactly. It is defined as the distance from the boundary. It is the distance from the boundary in which the velocity reaches 99% of the velocity of free stream. If the velocity is here, that is u, then this here the velocity at this point, the velocity is equal to 99% of this free stream velocity, that is 0.99 u. Then at this distance from the boundary surface is called delta, that is called boundary layer thickness. Okay. Next is the displacement thickness. What is displacement thickness? It may be defined as the distance measured perpendicular to the boundary of the solid body. Okay, perpendicular of the solid body, by which the boundary should be displaced. This boundary should be displaced to compensate for the reduction in flow rate of the flowing fluid on account of boundary layer formation. Okay, that already know that due to this boundary layer, due to this boundary surface, okay, there will be retardation of the flow. There will be reduction of flow velocity in the boundary layer. In the boundary layer, there will be reduction of flow velocity. There will be retardation. So due to this retardation, there will be reduction in flow rate. Okay. So to compensate this flow rate, okay, if the boundary can be displaced, okay, the boundary can be displaced, it can move in this direction, okay, and that displacement for after which the flow rate can be compensated, and that displacement which is perpendicular to this boundary, okay, this displacement, okay, which is actually virtual, just I am thinking that is a virtual, okay, so that displacement is called displacement thickness. Okay, so this displacement thickness, again I am repeating that it is measured perpendicular to the boundary of the solid body, that is the boundary of the solid body in this direction, by which the boundary should be displaced. It should be displaced. If it is displaced, okay, then obviously this boundary layer will gradually fluid. Okay. So there, so that it can be displaced, so that that can compensate for the reduction in flow rate of the flowing fluid. Okay, that displacement is called displacement thickness. Okay, so if let there is no plate, let there is no boundary, then flow velocity must be u everywhere, same flow velocity. But here, see, due to this boundary surface, there will be boundary layer and there will be retardation, and here the velocity will be less than this u free stream velocity, which should be if there will be no plate. And due to this boundary surface, due to reduction of the velocity, there will be reduction in flow rate. To compensate that flow rate, if we can displace this boundary, to compensate that flow rate, if you can displace the boundary, that displacement is called displacement thickness. Okay, so the mass rate flow through elementary strip if plates were not there. Just for the derivation, I have taken a small stream. Okay, this stream I have taken small thickness of dy. If there is no strip, no plate, okay, there is no plate, then mass rate of flow will be rho into u, capital U into dy, assuming unit width. This is the width of the plate, and this is the b is the thickness. Okay, but thickness we are considering unit width. Okay, unit width we are considering, so it will be density into velocity into thickness. Density into volume is the mass per unit rate, and density into velocity into dy. Okay, that will give you the mass per this time if we assume the width as unit. So this capital U I consider if there is no plate. Due to the boundary layer formation, there will be reduction in mass flow rate, because here the velocity is small u, not capital U. So the reduction will be this capital U minus small u into rho into dy. So total reduction, since I have considered the small thickness for dy, and if I take full thickness, full boundary layer thickness, that 0 to delta, from 0 to delta here, then it will be integration of 0 to delta rho all into u minus small u into dy. Okay, let to compensate, this is the reduction of mass flow rate. To compensate this value, we have displaced this plate perpendicular in perpendicular direction. If we displace, our displacement is, it is delta star. Delta star is the distance by which plate is displaced. Then the total mass flow rate due to this capital U. If you can displace, then this boundary layer will be displaced by this delta star. Okay, if plate can be displaced, then this layer will be displaced. So the total mass flow rate will be rho u delta star. So here, if it can displaced, then here the velocity here will be capital U. So rho u into delta star will be the total mass flow rate. So since we are compensating by displaced, if we can compensate fully of this value, then we have to equate this. This is the loss, and this is the displacement. Okay, which compensate this loss. So both are equal. So this integration of 0 to delta rho into u capital U minus small u into dy is equal to rho into capital U into delta star. So delta star is equal to integration of 0 to delta 1 minus small u by capital U whole into dy. So this is called displacement thickness. This is the expression for displacement thickness. If we know the velocity small u, if you know the expression of this bound velocity in terms of capital U, okay, we can determine this capital in this delta. Next is the momentum thickness. It is similar to this displacement thickness. Only difference is that here momentum is compensated. It is defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for the reduction in momentum of the flowing fluid on account of boundary layer formation. Total loss of momentum per unit time. Total loss will be, for momentum it will be rho into small u into capital U minus small u into dy. This is the loss of momentum. Let theta the distance by which plate is displaced. Okay. Actually, this is the mass. Loss of rate into u minus small u. So the momentum will be into velocity. That is the small u. Okay, small u. And total momentum through theta. If you displace, then total momentum will be through this theta, through this theta thickness. It will be rho into theta into capital U square, and which will be equal because it is this value is compensating this value. So both are equal. So if, after simplifying, we can get theta, that is momentum thickness, is equal to integration of 0 to delta u by capital U whole into 1 minus small u by capital U into dy. So this is the expression for momentum thickness. Similarly, energy thickness. Here energy, the kinetic energy is compensated. It is defined as the distance measured perpendicular to the boundary should be displaced to compensate for the reduction in kinetic energy of the flowing fluid on account of boundary layer formation. Okay, so again I am repeating, on account of boundary layer formation there will be retardation. Due to retardation there will be reduction in this velocity. Okay, and due to this reduction in velocity there will be loss of the kinetic energy. And how much loss? This is the 0 to delta half into rho into small u into whole u square minus small u square dy. This is the reduction in velocity. Let delta E is the distance by which the plate is displaced, compensated for the reduction in kinetic energy. For the reduction of the kinetic energy, if the plate is displaced by delta E, so kinetic energy through this delta E will be equal to 1/2 of rho into capital U into delta E into U square. Okay, so if you, since this value is equating, this compensating this value, so this both will be equal, so it will be equal. So delta E, after simplifying, we can get this U by capital U whole into 1 minus U square by capital U square dy. Okay, so this is about energy thickness. So we discussed about displacement thickness, momentum thickness, and energy thickness. Next, comparison between this thickness. Okay, one is displacement thickness, momentum thickness, kinetic energy thickness. This is the boundary layer thickness. Okay, so if you compare the values of this all this thickness, it is found that the delta E, that the energy thickness is less than the momentum thickness, which is less than the displacement thickness, which is less than the boundary layer thickness. Okay, this you have to remember. Okay, let's solve one example. The velocity distribution in the boundary layer is given. Here the velocity distribution is given, that is u by capital U, which is 3 by 2 y by delta minus y 1 by 2 y square by delta square, where y is the boundary layer thickness. So this is given. We have to calculate delta star by delta and theta by delta, ratio of displacement thickness with the boundary layer thickness and ratio of momentum thickness with the boundary layer thickness. Okay, so first this boundary layer thickness, displacement thickness, the expression is integration 0 to delta 1 minus small u by capital U dy. So here if you can put this is just simply the integration, just 0 to delta. If simply integration you can do, and that delta by w, which delta star by delta will be 1 by 12. That is the answer. Similarly for theta is u by capital into 1 minus y u by u. Okay, whole integration. Then you have to put this u by u value expression here and here. Then we can just multiply and integration we can do, and the final value will become 19 by 120 delta. So theta by delta will be 19 by 120. So this is the answer for this ratio of momentum thickness and boundary layer thickness. So here, so today class we discussed about this boundary layer concept, about the characteristics of the boundary layer, about the displacement thickness, momentum thickness, energy thickness. Okay. So for today class, this much. Thank you so much.